Hi calculus students. In the previous video we used this graph of f of x or f of t in order to find the values of the integral function g of x. So we used the area bounded by the curve to fill in this table of values, and then we plotted these points on the table on the next page. So in this video we're going to figure out how to determine when is g of x increasing, decreasing, concave up, and concave down in order to get an accurate graph. We are going to add some notes under here. And the main note that I want you to know is that, if g of x is equal to the integral from 0 to x of f of t dt, and this is what I'm given in the line, in the directions. So they told us this. Then I know that if I take the derivative of both sides, then the derivative of g is equal to, I know that the integral is the antiderivative, so that when I take the derivative of the integral, I'm just going to get my f of x. It ends up being f of x, not f of t, and we will talk a little bit more of that in our next unit. But I know this is true, so I'm telling you this, which in sum tells us that f is the derivative of g. Okay, this is a really important note. So we already know how the graphs of derivatives relate to the original function, and we're going to use that same knowledge to relate g with f. Okay, so we already have a lot of background information about how these things relate. So this point right here is key. F is the derivative of g. Okay, so since g is the integral and f is the original, I know that f is the derivative of g. And we're going to use this information to help us answer these questions to better know what the graph looks like. Okay, so the first question, so I'm just gonna write this here because I really want you to remember it. F is the derivative of g, exclamation point, exclamation point, exclamation point. So when I'm asked on what intervals is the graph of g increasing, I know that since f is the derivative of g, I'm just going to have to figure out where f is positive. So I can say, and I hope that you are looking at your graph at the same time, so you should still have your graph out to understand what I'm talking about. So I know that g is going to be increasing from -1 to 3 because that's where f is greater than 0. So we're using the same logic that we used back when we learned about how the graphs of the derivative relate to the original function. Okay? And then on what intervals is the graph of g decreasing? I will say from -3 to -1 in union with 3 to 7, and that's because f is less than 0. F is negative. So if I flip back here, that should check out. So the places where the graph is negative, right here, is where g is going to be decreasing because f is the derivative of g. And then the place where the graph is positive, where f is positive, g is going to be increasing. Okay? Alright, and we can use similar strategies to answer the rest. So on what intervals is g concave up? I know that g is going to be concave up because f is increasing. So anywhere where f is increasing is where g is going to be concave up. Okay? We've used this strategy before. So those intervals are -2 to 1 in union with 5 to 7. And then the other way, I know that g is going to be concave down because f is decreasing. This is kind of like my justification. And so wherever f is decreasing is where g is concave down. So this is from -3 to 2 in union with 2 to 4. Those are all our important information, and we can use what we just wrote to determine the rest of the stuff. So how would we determine where G has a local minimum? We would say G has a minimum when its derivative changes from negative to positive, and its derivative is f. So I'll say when G prime, which is f, changes from negative to positive. And if you look at the graph, you'll see that this never happens. It doesn't ever change from negative to positive. So there are no minimum values on this graph. And then the opposite is true for it to have a local maximum. I would say G has a local max when G prime, which equals f, changes from positive to negative. Hopefully you get my symbology. And this does happen on our graph. So looking back at our graph, where does G prime change from positive to negative? Oh wait, sorry, I kind of lied to you before. Did anyone notice my mistake? It does change from negative to positive right there. Oh no. So there is a min, and then there's a max right there. Oopsie daisies. Haha. Okay, so there is a minimum at x equals -1, and there's a maximum at 3. Did any of you catch me? Good job if you did. Excellent job. I'm glad I looked back at the graph. So there is a minimum at x equals, what is it, -1? And there's a max, and these are all local values, remember, they're local. Local max at x equals 3. Cool. And then finally, how can you use the graph of f to determine where G has a point of inflection? So G has a point of inflection, inflection, when G changes concavity. This occurs when its derivative, so when G prime, which equals f, changes from increasing to decreasing or decreasing to increasing. So I'll just write increasing, like INC, that means increasing to decreasing, or decreasing to increasing. I'm going to write these abbreviations because I know what it means. If you think you'll get confused, just write out the full word. And so the place where that happens is only at x equals -2. Okay, so that's the only place where it actually changes from like decreasing to increasing. The other places where it kind of changes, like here, it changes from increasing to 0, so it's not really changing to decreasing, so that's not a point of concavity. And then similarly here at 4, it changes from decreasing and then just has a slope of 0, so that doesn't actually have a inflection point right there. But we're going to use all that information we just found to now fill in this graph. So I'm going to show you how I would fill this beautiful graph in, and then you can kind of check to make sure it looks good, if you agree with it. So I know I have an inflection point here, so it changes from concave down to concave up. So then it's concave up to right here. Here the slope kind of like levels out at 1. And then it's concave down, has a maximum value at 3. Concave down, the slope is pretty much equal to 1 right there again. And then it is concave up for the rest of the function. Okay, so I recommend that you really compare the values of my purple graph of g, so this is the graph of g of x, to the values of f to figure out how I chose when it should be increasing, when it should be concave up or concave down, or these kind of unique places where it's neither concave up nor concave down because of the zero slopes right there. Okay, so that's the end of this video. Make sure you understand it before moving to the next one.